Hello, welcome to my talk all about the fluids. This talk is the first part of the topic of dimensional analysis. In this part, the principle of dimensional analysis will be presented, and discussions will be on why we need to conduct a dimensional analysis for the problem and how we can carry out a dimensional analysis. Let's start from an example of viscous flow in a horizontal pipe. This is a famous example we have seen in many textbooks of flow mechanics. When the flow velocity is small, the corresponding Reynolds number is small, say less than 2,300. The flow in the pipe can be regarded as nominal, and an analytical solution can be obtained as the Hagen-Poiseuille flow. However, when the flow Reynolds number is increased to a very large number, say 10 million, the flow in the pipe would be fully turbulent, and there is no analytic solution for such a flow. It is interesting to note, when we talk about the flow in the horizontal pipe, why we relate the flow with Reynolds number rather than the individual physical parameters, such as the diameter of the pipe, the velocity of the fluid viscosity, etc. It will be seen this is the result of a dimensional analysis for this specific problem. When studying a flow in the horizontal pipe, especially for the turbulent flow, we can either get the flow using the numerical modeling or using an experiment. In both ways, we may look at the parameters which will cause changes of the fluid friction. From the experience, the fluid friction may be affected by the fluid velocity, since a large flow velocity may cause a large fluid friction. The fluid friction is very relevant with the fluid viscosity, and the friction is also dependent on the fluid density, and the pipe diameter would have effect on the fluid friction. In fact, there is an important factor called the roughness of the pipe. It's very relevant to the fluid friction, especially in the turbulent flow. However, for simplicity of the analysis, the pipe roughness is excluded in the analysis in this talk. As such, the fluid friction can be expressed as a function of 4 physical parameters given by this. If we make a direct analysis, we can see from the function we need to change all 4 parameters to examine how these parameters affect the flow friction. In an experiment, we can change the fluid velocity. For instance, for changing the flow rate of the flow passing the pipe. And we can change the fluid viscosity by using different fluids. However, this may change the fluid density as well. Changing the viscosity and changing the fluid density would be coupled together. And if we want to change the diameter, we need to use different model. So we can see for changing all these parameters, it is not easy. The easiest way is changing the fluid velocity. If we use numerical modeling for studying the problem, we may not have such difficulties as those found in the experiment study. But we have to generate the relevant data based on the changes of the parameters. Once we have the required data, we may have another difficulty on how we can find a good way to link the 4 parameters and the fluid friction. Thus, we may ask a question: is there a better way for carrying out the study? The answer for this question is yes. And the answer is the dimensional analysis, including the relevant implementation method, Buckingham Pi Theorem. Dimensional analysis is a method for analyzing the relations between different physical parameters and identifying the base unit and independent variables, such as mass, length, time, temperature, etc. Dimensional analysis can be also used to check the relations between the physical quantities that are involved in the phenomenon of interest. In the Buckingham Pi Theorem, if there is a physical meaningful function involved n physical variables and m physical dimensions, then the original equation can be rewritten in terms of a set of p equaling to n minus m dimensionless parameters, termed as pi 1, pi 2, and pi p, which can be constructed from the original variables. The Buckingham Pi Theorem could provide a method for computing the relevant dimensionless parameters from the given variables, even if the detailed form of the function is still unknown. In dimensional analysis and the Buckingham Pi Theorem, it is important to identify the base unit and dimensions involving in the problem. Principally, there will always be a unit for physical parameters, except those non-dimensional parameters or numbers. Thus, in reality, we may have many different units for different physical parameters. However, there are only 7 base units in total, and 4 of them might be used in fluid dynamics. These base units include mass, m, the unit kg, and length, L, unit meter, and time, T, unit second, and temperature, theta, unit Kelvin. And we have also other 3 base units used in different subjects, which are including the electrical current, I, unit ampere, the luminous intensity, C, unit candela, and the amount of substance, N, unit mole. These 7 base units are defined by the International System of Units, SI, and all other units can be derived from these 7 base units. In this slide, simple examples would show the derived units. For instance, an acceleration is given by the second-order differentiation of the position with regard to time, and thus the derived unit is given by meter per second square with the symbol Lt power of minus 2. The force is calculated based on the Newton's second law of motion. Its unit is Newton, N. However, it is a derived unit with the symbol m L T power of minus 2. All equations for any physical parameters must have same dimensions at both sides. Such a principle can be frequently used for checking whether the mathematical equation is correct in terms of dimensions, and this can be very useful, especially for those complicated equations. And this is a simple application for dimensional analysis. Now, in this slide, we will see how we can use Buckingham Pi Theorem to analyze the problem. The first step is to analyze the problem and identify the parameters involving the phenomenon of interest. Suppose we have n variables x1, x2, xn, then the parameter of interest can be expressed as a function of other n-1 variables as this. The second step is to confirm the dimensions involving the problem m. For instance, for most problems of fluid dynamics, they involve 3 dimensions: mass, length, and time. If the fluid dynamic problem involves in energy or heat transfer, then the independent dimension temperature must be included. For a system with the total variables n and the independent dimensions m, then the problem can be determined using n minus m non-dimensional parameters termed as pi 1, pi 2, and pi n minus m, and the function can be constructed using the independent variables and the relevant variable. It will be seen this dimensional analysis could simplify the problem a great deal. After dimensional analysis, the problem can be expressed as a function of non-dimensional parameters as this. The third step, we need to construct n-1n non-dimensional parameters, pi 1, pi 2, etc. Use the relevant parameters as this. And the number A, B, and C are chosen so as to make all pi's dimensionless. Now let's go back to the problem at the very beginning and use the dimensional analysis for the fluid friction in a horizontal pipe. Based on the analysis we made, we can identify 5 physical variables. So n equals to 5. This includes the fluid friction, fluid velocity, fluid viscosity, fluid density, and the diameter of the pipe. And there will be 3 base units: they are mass, length, and time. So m equals to 3. And we can also make the dimensions analysis for the variables. Based on the above analysis, we can determine the number of the independent dimensions, or the non-dimensional group. N minus m equals to 2, so we will have 2 dimensionless parameters, pi 1 and pi 2. After that, we need to construct the non-dimensional groups as this. And then the function can be reduced as this. So you can see, after the dimensional analysis, the function of 4 physical variables is reduced to a function of 1 non-dimensional parameter. As such, the problem can be much simplified. In this slide, a simple result of the dimensional analysis is given. So, the dimensional analysis will give the 2 dimensionless parameters, pi 1, pi 2, as this. Pi 1 is actually the friction coefficient, and the pi 2 is corresponding to the Reynolds number. So after this, the equation of the problem can be written as this. The friction coefficient is a function of Reynolds number only. So we can see after dimensional analysis, the problem is much simplified. And in this case, we only need to adjust the fluid velocity to get a different Reynolds number, rather than changing all individual parameters. As an example, this plot is a relation of the friction coefficient and the Reynolds number. So in this plot, we can see there will be 3 regions: nominal flow, translational flow, and the fully turbulent flow.